Okay, so what I am going to do now is to tell you the fundamental theorems that you can obtain, the first theorems that you can obtain about classification of Riemann surfaces using covering space theory. Okay, so I will state the theorems, okay, so that you get a feel of what kind of results you can expect, and then later on we can start proving these theorems. Okay, so let me begin like this. So here is a theorem. So I will just write it as a first classification of Riemann surfaces. So as I was telling you the last time, that any Riemann surface admits a universal covering, which also becomes a Riemann surface, and the universal covering is simply connected. So the universal covering has to either be it has to be one of the three simply connected Riemann surfaces, namely the Riemann sphere, or the complex plane, or the upper half plane, which is the same as unit disk. Okay, so that means that every Riemann surface is going to be one of these three modulo certain subgroup of automorphisms, which are going to be Mobius transformations, and that subgroup is going to be isomorphic to the fundamental group of the Riemann surface that you are trying to study. Okay, of the Riemann surface whose covering space you are looking at. Okay, so I will discuss all the three cases. Okay, so let me write the first case. Let X be a Riemann surface. Okay, suppose the universal covering space of X is P1, namely the Riemann sphere. Okay, so suppose you take a Riemann surface, and suppose the universal covering space is P1. P1 is, of course, this is the Riemann sphere, the Riemann sphere. Okay, then X is isomorphic to the Riemann sphere itself. Okay, so in other words, the only Riemann surface which has universal covering space, the Riemann sphere, has to simply be the Riemann sphere. Okay, so you do not get anything in this case, right. So then therefore the next case that we have to look at is when the universal covering space is the complex plane. Okay, so of course again let me repeat, the universal covering space of X can either be the Riemann sphere, or it can be the complex plane, or it can be the unit disk, which is biholomorphic to the upper half plane. So let me consider the next case. Suppose the universal covering space of X is the complex plane. Okay, so this is the next case. Then what happens is that the fundamental group, the first fundamental group of X, has to necessarily be abelian. Okay, so that is a condition that will follow from covering space theory. Okay, and it has to be abelian, and it can be only certain possibilities, only one of three possibilities, which I am going to write down. So the three possibilities are, of course, the fundamental group is trivial, okay, which is the 0 group, or the fundamental group can be Z, or it can be Z direct from Z. There is no more freedom. Okay, so let me write this case. then the fundamental group pi 1 of x has to be abelian and in fact has to be isomorphic to the trivial group Z or Z direct sum C. Okay. And what do you get in these cases? If the fundamental group of x is 0, okay, of course sometimes we write just 0 or we write 0 with a bracket, it means the same thing, then x has to be just isomorphic to C. So whenever I write this isomorphism, I mean Biholomorphic isomorphism. It's an isomorphism as Riemann surfaces, okay, not just a topological isomorphism. It means isomorphism as Riemann surfaces. Mind you, we are trying to classify Riemann surfaces up to isomorphism. Okay, so all the isomorphisms I am talking about here are all isomorphisms as Riemann surfaces. So the first fundamental group is 0, then x has to be just the complex plane up to an isomorphism, holomorphic isomorphism. If the first fundamental group of x is Z, okay, then x has to be essentially a cylinder. It has to be a cylinder with the Riemann surface structure obtained by fixing a non-zero complex number and going the plane modulo integer translates of that non-zero complex number, which gives you, as I have told you in an earlier lecture, Riemann surface structure on the cylinder. So then x has to be just C star, okay, and of course you know the first fundamental group of C star is Z, okay, and the other possibility is that if the first fundamental group of x is Z direct sum Z, okay, if the first fundamental group of x is Z direct sum Z, then x has to be isomorphic to a complex torus, okay, then x is isomorphic to a complex torus, okay. So by a complex torus, of course I mean you take two non-zero complex numbers which as vectors are linearly independent over R, so that they are the coterminus, you take the parallelogram that they form in the complex plane, and then you are essentially looking at the complex plane modulo translations by integer multiples of these two complex numbers, and as you know that is going to give a Riemann surface structure on the torus, okay, and that is what I call as a complex torus. So x is isomorphic to a complex torus, okay, but of course please also remember at this point that when I say x is isomorphic to a complex torus, it could be different complex tori, okay. So there is a point of view that if you look at various non-isomorphic complex tori structures that you can put on a real torus, I told you there can be many, and in fact I told you that there are as many as complex numbers, please remember. So at this point what I want to stress is that you know when I say x is isomorphic to a complex torus, that complex torus could be one among many depending on x, okay. So these are the cases when the universal covering space is the complex plane, okay. Now the only thing that is left out is the case when the universal covering space is the upper half plane, which is the same as the unit disk. So let me write down this case, which is slightly more involved. Suppose the universal covering space of X is U, the upper half plane, which is the set of all complex numbers such that real part of the imaginary part of that complex number is greater than 0. This is upper half plane, okay, which is, by the way, isomorphic to the unit disk. You know that. You can always find a Mobius transformation that maps the open unit disk to an open half plane, okay. So this is a set of all Z belonging to C such that mod Z less than 1. This is the unit disk, okay. So this is the only case that is left when the universal covering space of X is the upper half plane, okay. Then we look at two cases, the case when the fundamental group is abelian and the case when the fundamental group is non-abelian, alright. So what happens again when the fundamental group is abelian, you get only two possibilities, okay, and these two possibilities are as follows. So let me continue here, maybe I will draw a line here somewhere. 3a, if pi 1 of x is abelian, then of course and pi 1 of x is 0, okay, then what you are going to get is again just the upper half plane or the unit disk. Always the case pi 1 is equal to 0 is always going to give you back the simply connected case. So so it is not hard to guess in all these cases whenever pi 1 is 0, okay, you have to get the universal cover. So that is what is happening. So then X is isomorphic to just U, which is isomorphic to delta. 3b, if pi 1 of x is abelian and pi 1 of x is isomorphic to Z, okay, then X is isomorphic to either delta star, which is delta minus the punctured unit disk, okay, or X is isomorphic to delta sub r. This is the annulus with outer radius 1, inner radius r less than 1, okay. So this is the set of all Z in C such that r is less than mod Z is less than 1 for a unique r, a real number r belonging to the open interval 0 1, okay. So and of course the point I am trying to say is that you can ask whether there are any other possibilities. There are no other possibilities. So if pi 1 is abelian, these are the only two possibilities, and in some sense what this means is that you take a Riemann surface with pi 1 isomorphic to Z direct sum Z, that forces that the universal covering space has to be C and your Riemann surface has to be a torus, complex torus, okay. So what is the power of such a statement? The power of such a statement is one can define what is meant by an arbitrary Riemann surface structure, okay, just using the general definition of a Riemann surface. What is a guarantee that any other Riemann surface structure on the real torus has to be of this form? See, a general Riemann surface structure on the torus could have been anything, but the beautiful thing is the underlying topological space, the fundamental group depends only on the underlying topological space. So even if I had put some other Riemann surface structure on the complex torus, its fundamental group being still Z direct sum Z, that will force that the covering space is C, okay, because that is this is the only case where you get Z direct sum Z, okay, and then this theorem will tell you that it is the Riemann surface structure that you have put has to be some complex torus structure gotten by fixing two non-zero complex numbers, you know, which are linearly independent over reals, okay. So this is the amazing power of this theorem, okay. So that is what you must realize. So somehow the property of the underlying topological space of the Riemann surface being a torus, okay, that forces the condition that there is no other way of getting a complex Riemann surface structure other than the way you got it for a complex torus. So that is the power of the theorem, that is the power of the statement, okay, that is what you have to realize, okay. Then of course the situation when and of course you know, let me also add that if you change R here, then the delta R also changes in its isomorphism class. In fact, if you take two different R's, then the delta R's are not biholomorphic, they are not biholomorphic, okay. So you change the radius, then it will be in a different holomorphic isomorphism class, okay. That is the reason I say for a unique R, okay. So then the other thing that I am left out with 3C, if pi 1 of x is not abelian, if pi 1 of x is not abelian, then and if you then this is the left out case, and of course I am assuming x is compact, and what this case will cover will be all the complex structures that you can put on g dimensional tori, okay. So so let me write that if pi 1 of x is not abelian, then x is isomorphic to a complex, a Riemann surface structure on so I will put this in bracket, okay, let me remove the brackets. X is isomorphic to a Riemann surface structure on a G torus so a G torus is, you know, something that's that is gotten by taking you know G copies of a torus. You take G copies of the real torus 1, 2 and so on up to G, and what you do is you join them, you stick them together, namely you cut out an open disk here, you cut out an open disk there, and then the boundaries of this, the boundary circles of these two open disks, you just stick them, okay, and what you get is a G torus is something that will look like this. So this is a G torus. So if pi 1 is not abelian, and of course I am assuming X is compact, then you get a Riemann surface structure on a g-torus, right. So this is the first classification, and what it tells you is that somehow you can see that it's a kind of clue that it's better if we start by looking at Riemann surface structures on a topological space whose fundamental group is abelian, okay. So because the abelian case puts a lot of restrictions, okay, and essentially and of course I should say g greater than 1, because g equal to 1 is the case of a torus, okay, and if g is equal to 1, then the fundamental group is z cross z directs from z, and that's certainly abelian, okay. So when I say it's not abelian, g has to be greater than 1, okay. So this is what you get, this is what you can get, and the way one proves this theorem is basically if by assuming you do some covering, you assume the fundamental uniformization theorem for simply connected surfaces, which is actually which is essentially the statement 1 2, if I want I can call this as 2a 2b 2c, so it is 1 2a and 3a, okay, essentially. So if you assume the fundamental uniformization theorem, which says that the only simply connected Riemann surfaces are either the Riemann sphere or the complex plane or the unit disk, or which is the same as upper half plane, if you assume that, and then you use properties of universal coverings and covering spaces, okay, and you also use study Mobius transformations, okay, then you can deduce the rest of the statements. So I'll write that down. So all these statements can be deduced using deduced from the uniformization for simply connected Riemann surfaces, which is essentially 1 2a and 3a, namely 1 2a and 3a, okay, using the theory of covering spaces and properties of Mobius transformations. Okay, so this is the key to proving all the statements in the theorem. So you divide the proof of this whole theorem into two pieces. The first statements are essentially the fundamental theorem, uniformization of simply connected Riemann surfaces. You assume that, and the rest of the statements can be gotten by covering space theory and by studying Mobius transformations. So this is what we will do in the forthcoming lectures, okay. And then of course what will remain is to prove the fundamental uniformization theorem, that is the uniformization for the simply connected Riemann surfaces. That will involve some more work, some analysis will be involved in that, and we will do that as well, okay. So so this is one aspect of so this is to give you an idea of what kind of theorems you can expect, because you see whenever we have structures in mathematics of a certain type, you are always interested in finding out what happens to the isomorphism classes. I mean, how will you distinguish one structure from the other? So this basic classification problem that always comes in, and this is how a first solution looks like. Okay, but then there are but you can see that this is a, in some sense this is a coarse classification, because in some sense it is a classification that basically involves only the fundamental group. Okay, roughly you see everything is controlled by the fundamental group of the underlying real surface. Okay, but then we need to have a finer classification. For example, you take a Riemann surface with fundamental group z directs from z, okay, then it could be any complex torus, and there are complex tori which are not isomorphic to each other. So among these complex tori you still have to do a classification, and trying to understand that is what leads you to study various complex structures on a real torus. Okay, and such a problem is an example of a moduli problem. So you have an underlying object and you put new structures on that, and then you want to see how many different structures you get. So you take a real torus, okay, and you make it into a Riemann surface. There are so many ways of making it into a Riemann surface, and then the moduli problem will tell you that if you take the set of isomorphism classes of Riemann surface structures on a real torus, okay, that is various structures of this type, then that is, I told you, that is bijective to the complex numbers, and in fact I told you that set itself acquires the structure of a Riemann surface. Okay, so it's amazing, and a similar thing happens also with Riemann surfaces of this type. These are compact Riemann surfaces. After all, you can see this is clearly compact as a manifold, compact as a topological space. So I haven't yet discussed what a manifold is, which I will do, but a Riemann surface is a one dimensional manifold in any case, complex manifold. I'll explain that later, but don't be worried about it. The point I want to make is that this is compact, okay, and trying to count how many independent complex parameters you need to classify all the different Riemann surface structures on this is part of the moduli problem for various Riemann surface structures that you can put on a certain g-torus, a real g-torus. Okay, when I say real, that means no Riemann surface structure has been fixed. Okay, and you are trying to put various Riemann surface structures, making it into a complex g-torus. Okay, and then you want to know what is if you take the set of isomorphism classes, is this going to give you something? So again, it's beautiful that it does give you a space, okay, and then this is a decent space. We can talk about the dimension of the space, and you know, dimension is in a very naive way, it is a number of independent parameters. Okay, and then if you calculate the dimension, there is a formula for the dimension which is known to Riemann. Okay, and that formula was justified in the 1960s. Okay, and that leads you into the problem of finer classification. So what I am trying to tell you is, the reason why I call this as a first classification is because there is still finer classification that needs to be done. Okay, and the finer classification essentially is done when you study moduli theory. Okay, so at least for the case of a complex torus, I will try to outline how you can do this finer classification, because it involves reasonably easy methods. But of course for genus G greater than 1, the methods are a little more advanced, and let's see if we can try to outline what happens in this case also. Okay, so what I am going to do next is I am going to tell you about, I am going to draw another diagram. I am going to rub out all this. I am going to draw another diagram trying to tell you to give you a pictorial view of this classification. So let me rub this off. So this is just to help you aid your memory, okay, to so you take Riemann surfaces, you can break them down into non-compact Riemann surfaces, and then you can break them down into the other possibility is their compact Riemann surfaces, okay. And I am going to look at several things. I am going to write here number of moduli and then I am going to write moduli space, then I am going to write universal covering, and then I am going to write first fundamental group, okay. So of course both in the non-compact and the compact case, the simplest is the case of simply connected surfaces, which is a fundamental example. So if I take the simply connected one, then if it is non-compact, you are going to get either the complex plane, or you will get the unit disk, which is the same as the upper half plane, okay. And in the so maybe I have to rewrite that so that it looks better. So let me write one line and then so maybe I should write it here. So let me write the non-simply connected ones. Let me write a few of them, which I am interested in, namely C star, delta star, delta r, okay. And you see for all these cases, if I look at so I put here the number of moduli, and then I put the moduli space, and then I put universal covering, and then I put pi 1. So if you look at it, roughly the moduli space is supposed to be the set of isomorphism classes of Riemann surface structures of that particular type, okay. So if I look at the complex plane, it means look at the set of isomorphism classes of Riemann surface structures on the complex plane, and you know that on the complex plane actually I can put two Riemann surfaces. I can force the structure of the unit disk on the complex plane, and that will not be isomorphic to the complex plane, okay. So if you look at the if you fix the underlying surface to be R2, okay, then you will essentially get two Riemann surface structures, okay. So what happens is that you get a degenerate situation. So in this case the so let me draw a line here. So in this case what happens is the first fundamental group is, of course, for both the first fundamental group is 0, that is because both are simply connected, okay, and both are simply connected. So the universal coverings are themselves, okay. So the universal covering for C is just C, the universal covering for delta has to be delta, okay. Mind you, these two are homeomorphic, okay, but as holomorphic universal coverings, they are not the same, because the holomorphic structures are all different. So see, whenever I am talking about universal coverings, mind you, these are all universal coverings in the holomorphic sense, okay, because I told you if you take a Riemann surface and you take the underlying topological space, take the universal covering, then because the underlying topological space below has a Riemann surface structure, and because the universal covering is a local homeomorphism, you can transport the Riemann surface structure locally to the space above, and in that way you can make the space above, the covering space, you can make it into another Riemann surface. So whenever I say universal covering of a Riemann surface, it means that the top space is also a Riemann surface in a unique way such that the covering map is a holomorphic map, okay. So please remember that. So in this case the universal covering is complex plane, here it is the unit disk, and the number of moduli, so the number of moduli is defined in the following way. Whenever you take the set of isomorphism classes, and if that set is discrete, for a discrete set we never define dimension, okay, we always think of it as being of dimension 0, okay. So usually the number of moduli is defined to be the dimension of a moduli space, and a moduli space is some nice structure on the set of isomorphism classes of Riemann surface structures on a given topological space, okay. So in this case what happens is that the underlying structure is just the plane, okay. So if you take the set of isomorphism classes, you will get only 2 points, you will get one equivalence class that corresponds to this, another equivalence class that corresponds to that. So the moduli space will contain only 2 points, okay, and then the number of moduli is we agreed that if there are only if the moduli space is discrete, you better give the number of moduli, you better give it as 0, because it should be the dimension, okay. The dimension of a discrete set should always be 0. So excuse me, so so in this case what happens is I'll basically get moduli 0, okay, and the moduli space is just consisting of, it's a set consisting of just two two elements. So it's just going to be these two elements, and when I put the bracket I mean holomorphic isomorphism class. So here what I am doing is I am looking at Riemann surface structures on R2, and there are only 2 I can put, okay, there are only 2 Riemann surface structures on R2, okay. So so mind you, when I am talking about moduli space, basically I am fixing the underlying topological space, and then I am looking at isomorphism classes of Riemann surface structures that you can put on the topological space, okay. So in this case it is R2, mind you these two are both homeomorphic to R2, okay. If you go back to example 1 and 2 you will notice that, and there are but these two are not holomorphic, which you know already, okay. So this is the story for this is a very simple case. Then in the case of C star, delta R, and of course there are further examples, I am just giving some examples. So in each of these cases the fundamental group is always Z, the fundamental group is the same for all of them, okay, and all of them are homeomorphic, they are all homeomorphic, okay. So in this case if you look at the if you look at the universal coverings, the universal coverings are all going to be different. So for C star the universal covering is C, for delta star the universal covering is delta, for delta R also universal covering is delta, and mind you delta is the same as U, okay. So U will be the universal covering, or delta will be the universal covering for these two, whereas C will be the universal covering for C star, okay. And in this case if you look at the number of moduli, I will write it as one real parameter for the following reason, because the set of isomorphism classes of Riemann surface structures that you can put on one of these spaces, which are all anyway on one of these spaces which are all homeomorphic, if you think of them as the same topological space, then there are three possibilities. You get one isomorphic to C star, you get one isomorphic to delta star, okay, and then you also get these two are two discrete points, and then you get a continuous family, and that continuous family is the isomorphism class of the delta r's, okay, where r belongs to 0, 1. So this is what happens. And so if you look at the dimension of this, the only thing that will contribute to dimension is this real parameter varying over the interval, and therefore you get 1 as a real parameter, okay. And if you want to think of it as a complex parameter, you should treat it as half, okay, but let us not do that. Then I come to the case of compact Riemann surface. So again, so let me make space for writing that down. Let me write this in a little to the right. The compact case. So in the compact case, what happens is you have, first of all, again the simply connected, so the simply connected case, and then of course the next thing is one torus. Then you can go on dot dot dot, and then you have a g-torus, the way I have defined it here, okay. And what happens to this situation? When it is simply connected, of course the fundamental group is 0, okay, and the universal covering space is itself. So simply connected case is of course compact simply connected case is the Riemann sphere, it is just P1, it is a Riemann sphere, okay, and the universal covering is P1 itself, okay, and there is no you do not have any freedom now, so well, the number of moduli is 0 and the moduli space is single point, namely the isomorphism class of P1, that is all you get, okay. The next possibility is that of a one torus, this is a complex torus, okay, and what happens is that the fundamental group is z cross z, or z direction z is same as z cross z under addition, okay, and in this case what happens is the universal covering space is the complex plane, the universal covering space is the complex plane, and you are getting the complex structure on that torus by going modulo this group of translations by integer multiples of two non-zero complex numbers whose ratio is not real, okay, and in this case what happens is that the moduli space is C, okay, that was theorem that I told you. The set of isomorphism classes of complex structures on a one dimension on a one torus, which is S1 cross S1, okay, a real torus, is isomorphic to C, and that set actually acquires a Riemann surface structure, and as a Riemann surface it is isomorphic to C, and so the number of moduli will be one complex parameter. So let me write it as one complex parameter, okay, and so what is left out is the case of a g torus, okay. I have told you that if you go to a g torus g greater than 1, I told you the fundamental group is not abelian, okay, and in this case the universal covering space is the upper half plane, okay. So that is the, it comes in the third case in the statement of the theorem, which covered the case when the universal covering space is the upper half plane, okay. So the universal covering space is upper half plane, is the same as the unit disk, mind you. So wherever I write delta, I can also write u or delta, and of course here again it's delta or u, okay. And the beautiful thing is that there is a moduli space mg which was known to Riemann, and the only thing is that this moduli space had the structure of what is called as a complex analytic space, okay, and this is something that I will try to explain. But in any sense it's a decent space, and it depends on 3g minus 3 complex parameters, okay. So this is Riemann's formula. So Rayman in his amazing work says that the various isomorphism classes that you can of Riemann surface structures that you can put on a g-torus has to depend, if you construct it as a space, then that space viewed as a space over the complex numbers has to be of dimension 3g minus 3. So this is Riemann's formula, and of course to justify it there was, following Riemann, the work of Teichmüller and then the work of Lippmann, Beers and so on, who justified this formula, and now a proper proof of this formula is very accessible, okay, and I will see if I can try to give a proper proof of this formula, okay. So this is the picture of classification of Riemann surfaces, and the you must realize that the to begin with, to have said so much, the first classification is already very interesting, but actually today the field of research that is very active today is trying to study this object, a moduli space, okay, how to properly define it and then study its properties with respect to topology, with respect to analysis, and in so many ways, okay. So this is what is of current research interest, okay. So I will stop here.